Welcome to Quantum Photonics. I'm excited to introduce a groundbreaking advancement in the realm of data storage, poised to revolutionize AI computing in extreme environments. Imagine your smartphone never shutting down on a scorching day at the beach, or even more impressively, data storage devices operating flawlessly amidst the intense heat of a jet engine or the inhospitable surface of Venus. This once far fetched idea is rapidly becoming a reality thanks to the pioneering research by Deep Jariwala, our guest speaker, and Roy Olson of the University of Pennsylvania School of Engineering and Applied Science. In a recent publication in Nature Electronics, Jariwala and Olson's teams showcased a memory technology that can withstand temperatures up to 600 degrees centigrade and 1,112 degrees Fahrenheit, a temperature threshold more than double than that of any commercial storage devices available today. Remarkably, these devices maintain their integrity and performance for over 60 hours under these extreme conditions, demonstrating exceptional stability and reliability. And of course, our guest speaker will tell you more about this. And Deep is our favorite speaker here in Quantum Photonics. He's been here, I think now it's the fourth time that we've invited him. And we are always surprised that, right after he had made his presentation here, just a week or so after that, he is getting an award or is making a breakthrough. So it's just, a paradox on how he's doing that. So that's why I requested for his latest updated bio. So Deep Jariwala is an associate professor and the Peter and Susan Armstrong Distinguished Scholar in the Departments of Electrical and Systems Engineering and Material Science and Engineering at the UPenn. And his research interests broadly lie at the intersection of new material surface science and solid state devices for computing, sensing, optoelectronics, and energy harvesting applications. Deep completed his undergraduate degree in metallurgical engineering from the Indian Institute of Technology, Banaras Hindu University in 2010. Deep went on to pursue his PhD in material science and engineering at Northwestern University, graduating in 2015. At Northwestern, Deep made contributions to the study of charge transport and electronic applications of 2D semiconductors and their devices, for which he was awarded the Johannes and Julia Wirtman Doctoral Fellowship and the Hilliard Award of the department. Deep then moved to Caltech as a Resnick Prize postdoctoral fellow from 2015 to 2017, working on nanophotonic devices and ultra-thin solar cells before joining Penn in 2018 to launch his independent career. Deep's research has earned him awards of multiple professional societies, including the Adolph Lomb Medal of Optica, formerly OSA, the Peter Mark Memorial Award, and the Paul H. Holloway Award of the American Vacuum Society, the Richard L. Green Dissertation Award of the American Physical Society, the Army Research Office and Office of Naval Research Young Investigator Awards, Nanomaterials Young Investigator Award, TMS Frontiers in Materials Award, Intel Rising Star Award, IEEE Photonics Society Young Investigator Award, IEEE Nanotechnology Council Early Career Award, IEEE Benjamin Franklin Key Award, IUPAP Early Career Scientist Prize in Semiconductors, the Alfred Sloan Fellowship, in addition to being named in Forbes magazine list of 30 scientists under 30, and is then an invitee to Frontiers of Engineering Conference of the National Academy of Engineering. In 2022, his work on ferroelectric diode memory was also awarded with the prestigious Bell Labs Prize worth $100,000. And in addition, he also received the S. Reed Warren Jr. Award and Undergraduate Research Mentoring Award given to one faculty member every year at the Penn Engineering for inspiring and motivating undergraduate students through teaching research. He also serves as an associate editor for IEEE Photonics Technology Letters as well and as NPJ 2D Materials Applications. He has published over 150 journal papers with more than 20,000 citations and 10 patents. At Penn, he leads a research group comprising of more than 10 graduate and postdoc researchers supported by a variety of government agencies like the NSF, DARPA, ARO, AFOSR, ONR, and industries and private foundations. So, yeah, later on, I will be posting a copy of his Google Scholar link and also his website here at the room chat and also at my Twitter account as well. I had posted this already on my Facebook account. So, later, if you want to check more later, you can check my accounts on this. And I think, together with the YouTube channel, we are also starting to do a blog. And so you will get his bio also in the blog. So that will be a permanent reference for quantum photonic speakers. And so without further ado, I am bringing to you our very special guest speaker, Associate Professor Deep Jariwala. Deep, welcome again to Quantum Photonics.
Hi, thanks, Cecil, and welcome everyone. I should mention that I'm always honored and thankful that you invite me here and have really nice conversations with you all. In the past, the conversations have gone a little bit longer. Unfortunately, more recently, I have become a father, so I have a little baby at home. So, given the time frame, I won't be able to go for too long. I will be able to, hopefully be here for an hour, and after an hour, I will have to leave, unfortunately, to help with baby caring duties. So I hope all of you understand that and are understanding of my situation. Hopefully, we can find a longer conversation time another time, maybe schedule it in such a way that I will be able to talk more. So without further ado, let me jump into the presentation. I believe the slides have been posted by Cecile. The title slide is Turning Up the Heat in Data Storage. I will go over some of the slides which are trivial quickly. Like the second slide is just acknowledgement and support, thanking all the students, postdocs, and the funding agencies that support us. Without them, none of this work can be done. Should mention that a bulk of the work I'm presenting today has been supported by the Air Force. Right, so many thanks to the United States Air Force through their Office of Scientific Research as well as Air Force Research Lab. We are able to do all this cutting edge research that I'm presenting today. Slide 3 tells you the broad sort of a spread of my research group. One of the reasons I've come here multiple times is in the past I've spoken about electronic devices, solar cells, optoelectronic devices, and today memory devices. So these are all different topics. And so our group really plays into very different areas of research. But once again, the area that I'm going to be focusing on today is the top left corner, which is electronics area. And so if we move on to the fourth slide, even within electronics, we're going to have like very focused discussion today on like two major topics. First is I'm going to introduce the idea of ferroelectric nitride materials and the device concept of ferroelectric diodes. And then I will be introducing to you the main subject of the talk, which Cecile referred to in the introduction, which is high temperature non-volatile memory technology, which we believe we are the first ones to demonstrate it and are hoping to take it much forward. Okay, so with that, if I go to the fifth slide, the title is Dense Integration of Memory with Logic is Necessary. And so what do I mean by that? What I mean by that is if you look at the current computer architecture, a lot of the gains in computer architecture in the 80s and 90s were made thanks to Moore's law and Dennard's scaling law. But if you look at the revolution in computer architecture that has happened at least post 2010, that has largely been due to innovation at the architecture level and not necessarily at the device or scaling level. So even though Moore's law has technically continued, the real advances that people have gotten in terms of reducing energy consumption per unit useful computation has been through architectural innovation, which is what NVIDIA has done. I mean, one of the reasons why NVIDIA is such a valuable company today is because of its invention or coining the term GPU, which very cleverly arranges memory with logic and cleverly arranges parallel streams of computation as opposed to CPU, which does exact computations but sequentially, right? And so that's why I think has been the major player today. And so to go beyond today's best systems for computing, I think we will have to introduce novel materials and devices because we are approaching fundamental physical limitations of silicon on which most of computing is based. And so to do that, we will need the first element that I think we will need is we will need a novel memory technology, a memory technology that is non-volatile, which means it does not actively consume power, and that can be situated back end of line or on top of, say, the silicon microprocessor. So our group has been in search of these kind of memory technologies, and in prior discussions of quantum photonics, I've talked about this. Therefore, I won't go into too much detail on this. Again, just to save time and to get to the more important part. But if you look at back end of line memory technologies, there are several technologies out there. What we are focusing on and what we believe might be the winning technology here is a ferroelectric memory technology because it can meet all the key requirements that are required for this embedded non-volatile memory, which is low energy, high density, has to be fast, has to be back end of line compatible, so on and so forth, right? And so I think this is something that not all the technologies can meet. And we think ferroelectrics are best positioned to meet this. This is an old problem, 30, 40-year-old problem. All semiconductor industries have been trying to solve this. It's not an easy problem. Therefore, it is so hard to solve. But unlocking the problem opens up billions and billions of dollars worth of market value. So among ferroelectric materials, again, there are many competing materials out there. In fact, back in 2022, which is 2 years ago, the word ferroelectricity or the phenomena of ferroelectricity, I think, completed 100 years. So it's more than 100 years since this phenomena has been known. And PZT or lead zirconium titanate are like the classical ferroelectric materials. They have people have tried to commercialize them, but they have issues with silicon CMOS fab compatibility. You cannot scale them below 50 nanometers in thickness, and their course of field, so to speak, is too low, such that minor electrical fields or current pulses can lead to their depolarization or changing of the bits, or bits can flip. In other words, it will introduce errors in the stored data. The other one is hafnium oxide, which I would say is quite advanced today. It's Many industries are thinking of deploying it, but it also has its own challenges. Getting into the right ferroelectric phase over entire process wafers in a reliable way at processing temperatures that are compatible again with back end of line is very challenging. This has prevented Hafnia from being deployed, even though the first ferroelectricity in Hafnia was reported back in 2006. And the last one, which is aluminum scandium nitride, this is what we're focusing on. I don't necessarily think that this needs to be a material integrated in front end of line with silicon photonics, but I think this might be a revolutionary material for back end of line integration and for high temperature applications, which is what I'll be talking about. And so to discuss more aluminum scandium nitride, let's go to the next slide, which is slide 8. And the interesting thing about this material is that it's been out there for a while. I think it's been more than 15, 10 to 12 years now, at least, maybe even 15 years since aluminum scandium nitride was reported by the Japanese as a very superior piezoelectric material. And in fact, if you have bought a smartphone in the last 2 to 3 years, very likely it is inside your smartphone as a a piezoelectric BAW filter material. So if it has piezoelectricity, there were some people who were suspecting it should also have ferroelectricity. And so there are people searching for it, and the Germans in 2019 found that indeed it has ferroelectricity. And that's the journal reference shown in 2019 from Germany. It's, I think, Kiel University and the Fraunhofer Institute. They observed nearly ideal ferroelectric hysteresis loops with very large polarization. And the other interesting thing about this ferroelectric material is it's only exists in one stable, thermodynamically stable phase, which is the Wurtzite phase. It's the same phase or same crystal structure that you would think you have for gallium nitride, for example, or aluminum nitride, right? It's no different than that. It's a hexagonal crystalline material. And so the crystalline structure is such that you have in down polar position, the metal atoms are at the top, and in the up polar position, the nitrogen atoms are at the top, right? And so this is how it stores the electric field down, electric field up within the same material. Just like you would have in a magnet, it can be north-south or south-north. But here it is case for electric fields, and therefore it is called the ferroelectric and not ferromagnet, right? And so this is quite interesting. One, because the polarization is very large. Two, it can be extremely stable. There is no other phase that this material is stable in, so you don't have to do any phase engineering. It is foundry friendly material. A lot of times when people discover novel ferroelectric materials, they don't know how to put them into silicon manufacturing processes. But this is foundry friendly already. It's already in your phone, so it goes into chips, right? And so it has other superlative properties. Like if you go on slide 9, this is the review paper we wrote a while ago. A while is last year. There's too much stuff that happens every year. But what you can see over here is that we are comparing various ferroelectric materials on the left-hand side graph. And what you can observe is that this aluminum scandium nitride is ferroelectric is one of the largest polarizations and coercive fields concurrently. In other words, it's an extremely polar material. It can store a lot of charge in a very the stable manner, right? So which is good for many ways. There is also like bad things about it. Like for example, you don't want this high of a coercive field. So one of the aspects that scientists like myself and others are trying to engineer is to reduce the coercive field or the x-axis EC of this material to more manageable Manu values, which is like around 2 megavolts. If you look at its current value, it's like 4 megavolts. So we want to reduce that. So that is something that we definitely interested in doing. The other interesting thing over here is if you look at the right hand side graph, it actually is a material with a much lower dielectric constant, a low dielectric constant together with a large band gap as a ferroelectric material. And this actually makes it very suitable for low energy charging and discharging. Many times in ferroelectrics, such as, for example, the oxide ferroelectrics like PCT or SBT, which are mentioned on the upper side of the left right hand side graph, the dielectric constant values are so large that you have to expend a large amount of energy just to charge the material to then switch it. But if the dielectric constant is small, you don't have to spend as much energy to charge the material in order to switch it. So this is actually quite valuable in terms of low energy operation. And finally, as I mentioned earlier too, this material is back end of line compatible. In other words, you can deposit it at very low temperatures. The Japanese do it even at 100 degrees Celsius. So you can make a silicon chip, a microprocessor, NVIDIA GPU, Intel CPU, what have you. And then in the layers above the microprocessor, such as the metal interconnection layers, you can actually deposit this material as a memory device. Okay, so moving on to slide number 10, what I want to focus on is the ferrodiode devices that we made out of this material. There are, again, many, many, many types of ferroelectric devices that people make. I'm going to focus on the ferrodiode memory device. It's something that our group has pioneered here at UPenn over the past 3 years or so. And so if you go to slide 11, the ferrodiode memory device is like shown in a very simple way. It's actually very, very simple device. And I think the simplicity is what gives the research, the concept, its beauty or its applicability. You know, people like, especially when you go to industrial scale manufacturing, people like to do simple things. You make things more complex, people will refrain, or the cost will go up, or people will refrain from making things that are too complex. It just adds enormous levels of cost and complexity. And so, unless there is a market demand, people won't do it. So, it's a very simple device. It's just a stack, it's a sandwich structure of the top and bottom metal electrodes. In this case, they are platinum. And sandwiched in between is this ferroelectric material together with an non ferroelectric oxide material, for instance. And so if you look at the middle graphs over there, they are IV curves. They look like diode IV curves and log scale and linear scale. But what is important to note over here is that the polarity of diode is flipping depending on the polarization of the ferroelectric. In other words, the ferroelectric material is flipping the polarity of the diode, making it a memristor together with a diode like rectification function. So this is potentially useful for many things. I have discussed this in the past for many for compute and memory applications. This was one of the previous this is one of was one of the previous clubhouse chat that I hosted on. That was the concept that actually won the Bell Labs prize based on this material. So we used the ferroelectric diodes to demonstrate compute in memory, and you could do very fast, very efficient compute in memory without actually using transistors. So again, since I've covered that concept before, it's about 2 years old now. I don't want to go over it again. What I want to focus on is the new stuff. And the new stuff is that what else is aluminum scandium nitride good for, which is what is mentioned on slide 12. Actually, what you look when you look at, there's another thing that it's very the material stands out quite dramatically, which is if you look at the remnant polarization of the material as compared with the maximum temperature or the Curie temperature of the material, you see that it's at the top right corner, which means it's one of the most stable yet most polar ferroelectric material that we have found. So up to 1100 degrees Celsius, we have not seen ferroelectricity being lost in this material, which is remarkable. Right, and on top of that, it's a thin film material, which means you can put it down on silicon wafers or any other wafers and actually make devices out of it. And the reason I think this is very stable is because it's highly polar character. It's Woodside crystal structure. Woodside crystal structures are very thermodynamically stable crystal structures. And so the bonds are so strong, so ionic that it doesn't feel the need like it has to exist in any other state other than the ferroelectric state up to extremely high temperatures, right? So most other ferroelectrics, they turn into paraelectric materials when they go above a certain temperature. Like, for example, PZT turns paraelectric at 400 or 450 degrees Celsius. Same for hafnium oxide. You can consider this is analogous to, for example, if you have a magnet made of iron. Okay, so you have a magnet made of iron, you go home, put it on your refrigerator, it sticks. Try cooking up that piece of iron. If you cook it up to a certain temperature, if you take that piece of iron or magnet which is sticking to your refrigerator, once it goes above a certain critical temperature, it loses its magnetization. That critical temperature is known as the Curie temperature of the magnet. And so when it loses its magnetization, it becomes like a regular piece of iron. It won't stick to the wall of the refrigerator again. Right. Similarly, there is Curie temperatures for electric polarization, which is the Curie temperature for ferroelectrics. So that's what I'm saying over here, that once you program information into this material, to the temperatures up to 1100 degrees C that we and others have measured, it does not lose its polarization. Okay, because it's the Curie temperature, we don't know. It may be even higher than 1100 degrees Celsius. We don't know for sure. Maybe the material gets destroyed or obliterated before it stops being a ferroelectric, right? I think you have to actually thermally destroy the material before it loses information. It's that stable. Right? So this 1100 degrees Celsius stuff was done by Germans. They did that. They did it in like very, very thick material. So it's not really a device. They took a large, thick crystal of the material. They polarized it electrically. Then they put it in a furnace for a certain number of hours at 1100 degrees Celsius, took it out, and again measured the polarization. Right? I mean, that's a good, neat proof of concept, but you actually have to make devices that are integratable, device that can work. This is something that we went in and developed actually, and we are also hoping to commercialize them in the months and years to come. So going to the next slide, this basically brings me to the topic of high temperature non-volatile memory, why it is useful and why we are trying to make it using ferroelectric aluminum scandium nitride. Okay, so let's move on to slide number 14. Let me first talk about a review paper that we have written, and it will also come out in a high profile venue in the next 3 to 4 months, hopefully. And this is looking at materials challenges for extreme environment electronics. This is actually a very important research area. It's been around for 30, 40, 50 years since the space race or the Cold War began between US and Russia. This kind of research has been going on. But it's a very difficult research. It's not something that is easy to do. You need high temperature, high radiation environment, measurement equipment, things like that. And therefore, it's a difficult research to pursue, and therefore the community is pretty small. There are many, many challenges for doing electronics in extreme environments, high temperature and high radiation, or highly corrosive environments too. You have to figure out logic transistors first to actually do the computing. And within the logic transistors, you have to figure out gate dielectrics, semiconductors, right? Both of them, metal contacts and interconnects. They are another huge issue at elevated temperatures. They could melt, they could diffuse, right? Things like that. Bonding metals are also a huge issue. And then, of course, packaging is also a huge issue because you want the packaging to also survive elevated temperatures. So you have to do ceramic packaging, which is very unfriendly in terms of molding and bonding and things like that. But one piece that is often never discussed in the context of high temperature electronics is memory. And that's because it's a piece that people never paid that much attention to. It's also something that is very difficult to work on, as I will show you, right? But now more and more people are realizing it's important. And so the reason a lot of people did not pay attention to memory early on is because people were doing very simple computing applications in extreme environments, just measuring or sensing something and sending the information back out or something like that, right? So for example, in jet engines, in avionics, spacecraft avionics, or high-speed aircraft, supersonic aircraft avionics, planetary exploration like Venus, Mercury, for example, solar probes, deep well drilling, right? Automotives like inside engines and so on, inside nuclear power reactors and so on. All these places, people were just collecting very basic pieces of information. Now, with the requirement of more and more compact and higher functions of all of these things, people want to keep doing not only just the record information, but also process the information at elevated temperatures or in these harsh environments. And processing information means you have to collect some information, store some information, and then work on that information. So storing is really important then. And so keeping the memory away from the processor is no longer an option because otherwise your computation will also take forever. And plus, it's very well known that typically if you're operating something, an electronics, a sensor, or what have you, in a hot zone, and then there is a cold zone, and you're putting one part of the module in a cold zone, another part of the module in a hot zone, the main failure points are the connections between them, which are experiencing different temperatures on two different ends, right? And so, without a doubt, we need more complex computing in elevated temperature environment. So, if you go to slide 15, this is something that NASA and various other people have tried to work on for many years. One thing to keep in mind is this is something I teach in my lecture when I teach undergraduate semiconductor physics at Penn. Is silicon is the king at room temperature, but as soon as you take the temperature above 300 or 400 degrees Celsius, silicon is no longer the king. It's silicon carbide that becomes the king of high temperature, harsh environment electronics. And so this is reflected in these graphs. The first, the top right or A graph tells you something called as intrinsic carrier density, or amount of charge or amount of electrons that semiconductor material has as a function of temperature. And you don't want this number to be very large, but it does increase, of course, because increasing temperature, of course, injects more electrons in every semiconductor material. So if you look at silicon carbide is actually very well suited in this space. If you look at the black line over there, it's one of the lowest lying lines, even at elevated temperatures. And so people have tried to make transistor devices, logic transistor devices, out of silicon carbide and other, wide band gap semiconductor materials such as diamond, gallium oxide, gallium nitride. Right, these are all popular wide band gap semiconductor materials. People have done this for last 20, 30 years. And so the transistor space has been filled out quite well. The most successful among them, again, as you can see in the other three graphs, if you point look at the desired corners, are the blue dots. The blue dots are basically silicon carbide based transistors, JFETs. This JFET technology is the ruling technology today, and I think it will remain as a dominant ruling technology for high temperature logic or high temperature computation for the foreseeable future. And again, a lot of people don't appreciate what many of the US government agencies do. This is mostly thanks to NASA. As part of their efforts to send probes to the sun, to the Venus, and so on, NASA has taken on an effort over the last 20 years or so on how to make a Venus proof electronics. And so, to make Venus proof electronics, they decided it has to be made from silicon carbide. And so, they started developing these transistors. These transistors are not the typical field effect transistors, they are called junction FETs or JFET transistors. And so over the years, NASA has made and demonstrated JFET transistors. For example, on the left graph on slide 16, you can see that they have made and operated JFETs all the way up to 900 degrees Celsius, which is pretty cool, right? Of course, the on-off ratio is not very good at 900 degrees Celsius, but that happens to everything when you raise the temperature. But even if you consider like, up to 800 degrees Celsius, they can get an on-off of about 300 or so, which means you can do quite reliable computing up to 800 degrees Celsius without any problems. What you're seeing on the right-hand side of the screen, middle and the right-hand side, are basically the chips, the processor chips that NASA is making that can operate at these high temperatures. Right now, there's a chip designed from 2019. I think they have one on 2022 as well, which I don't have the picture of. But these are relatively small size chips. If you look at these are 3 by 3 millimeter and 5 by 5 millimeter chips. And if you look at these chips, there is not too much computing power on these chips. Actually, the computing power is very, very limited, situated mostly on the top side of these chips. The large columns or two black looking columns that you see on the chip, on the rightmost chip, they are basically SRAM memory cells. SRAM is static memory, so which means it does not hold information when you remove power to it. And so most of the computational capacity of these chips is very, very limited because a large number of transistors are just consumed to create the SRAM, static random access memory cells. And so the key question is, if you want to do any sort of complex computing, right? And complex computing means aside from just simply, taking the sensor data and pulling it out into the cold environment to be processed by another computer. Let's say you want to take the sensor data, interpret the sensor data, and act on the sensor data again, right? Like some kind of pattern recognition or interpretation, like very basic pattern matching function. You will need more complex, even if you want to multiply a few numbers or add or subtract a particular sensor data or a signal data that you got, right? You will have to find a way to store data and do more complex computing. And so, therefore, high temperature non-volatile memory will basically simplify this processor design to a great deal. So high temperature transistors are already available. They are well developed by NASA, but a high temperature memory is missing. And if you were to give a non-volatile memory, which means it does not actively consume power, and somehow pair it with this processor, it will change the game entirely for computing in these extreme environments. So this is what we have gone ahead and developed. If you go to slide 20, this is the prototypical devices that we have made and demonstrated. These are again made from aluminum scandium nitride material, as you may expect, because of its very high and very stable ferroelectricity at high temperatures. So the device is actually very, very simple. The device is a sandwich between nickel electrodes, platinum electrodes, and aluminum scandium nitride. It's a 45 nanometer thick film in between, right? And there are these circular devices that you see in the images below. We have just drawn these circles because they are easy to measure, but you can make them anything later on. Actually, circle is the most preferable geometry, and you can make them as small as possible, as large as possible. You want to make them as small as possible for high density memory. I mean, it's easy, we can easily make kilobyte to megabyte scale memory. I mean, for applications in those environments, you don't need gigabyte memory. Working memory of several kilobytes to megabyte is more than enough. Again, then the surface roughness or cross-sectional electron micrographs of these devices are shown in figure B and D, for instance. If you go to slide 18, I guess, sorry, I've been quoting the numbers wrong over here because they are a little bit messed up on my slide. But slide 18, you will see the electrical properties of these high temperature ferroelectric diodes, or these ferrodiode devices, we call them. These are DC electrical characteristics. Again, I don't want to go into too much detail, but the 1, 2, 3, 4 that you see in the top right graph, it tells you the voltage to current sweeps of these graphs, and you can see that 1 and 2 do not overlap with 3 and 4, right? Or 3 essentially. And that means that once you have crossed path 1 to 2, you have changed the state from a high resistance state to low resistance state. And so this hysteresis is basically a signature of memory, that if you follow path 1 to 2, you'll stay on one state. If you follow path 3, you are on the other state. And so this kind of hysteresis is maintained quite well. You can see the hysteresis all the way up to the brown curve, which is 600 degrees Celsius curve. And you can again isolate out various parameters from these curves, such as what is the coercive field, what is the on current, off current, and therefore on off ratio. To obtain a stable memory device or do stable computing, you want an on off ratio greater than 1, of course. And a ratio greater than 1 is what is the minimum required to do any computation. And so we get a stable ratio of more than 1 for up to 600 degrees Celsius. And in some recent unpublished data, we have even increased this number quite well of lately, which we have not published yet. And so this is, of course, DC measurements. One of the hallmarks of computing is fast operation. AC and pulse measurements are also necessary. So if you go to the next slide, which is slide 19, there we have shown the same thing working in AC measurements at 10 kilohertz, and then also pulsed measurements with 500 nanosecond pulses. You can see very sharp and clear switching of ferroelectricity up to 600 degrees Celsius. Once again, you can extract material parameters such as coercive fields or eminent polarization from this from these measurements. So again, proving without any iota of doubt that this is indeed ferroelectric switching that is stable up to 600 degrees Celsius. I should mention again, in unpublished data, we have demonstrated the same thing to happen all the way up to 900 degrees Celsius in these same devices. In the coming months or so, we will also end up publishing that data. But yeah, the 600 degrees C is like published value, but technically, as I said, you can keep jacking up the temperature. At the time, our capabilities to measure were only until 600 degrees C. Now we have capabilities to measure up to 900 degrees C, and we have seen stable ferroelectricity up to 900 degrees Celsius in these devices, and information retention for very long periods as well. Then, if you go to the next slide, which is slide 20, in these measurements, the important thing to then figure out is it's one thing to store information, but it's other thing to store information in a stable way. Today, if you go in the market and try to buy high temperature memory, people would sell you what is known as silicon flash memory. And that flash memory is rated up to 250 degrees Celsius. But even if you were to operate that memory at 250 degrees Celsius, what ends up happening is it loses information on the time scale of milliseconds. Within milliseconds, it loses information. So your circuits have to go and continuously refresh that information. This refreshing takes time. This refreshing is energy consuming, right? And it's not the best way to operate a memory, right? If you're refreshing things all the time, then what is it really a memory? Can it really store information, right? And so in this regard, I think you want something that is extremely stable for long periods of time, and you should not be able to disturb or destroy the information when you are going and reading the information. So one thing is you write the information, you store it in the memory, then you go and read the information and you read it over and over again. So for instance, let's say I have to store a program like an operating system, Windows or whatever, for a high temperature computer. I need the instruction set to be written into a memory that I can go and access repeatedly. Right? I cannot have it, be lost every time I turn off the computer. It has to be there somewhere. And so to do that, not only it has to be stable, it has to be stable to reading. It should not be the case that when you go and try to read it, it gets disturbed or destroyed. And so we have demonstrated that up to 1 million read cycles, it's again perfectly stable. Nothing happens to it. This million is just a number. million can be made a billion or a trillion or a quadrillion. I don't think it's going to change. It's just something that the students who are doing the experiment, they got tired after taking a million measurements. Of course, they are automated, but still, a million measurements will something that it keeps measuring and takes a few hours to measure it a million times. And once it was done, they are like, yeah, okay, you know what? It's not changing for a million times. It won't change for a billion or a quadrillion times. So they stopped it. Um, Similarly, for hours or time dependent measurements, they did these measurements up to 60 hours, and up to 60 hours, we did not see a long change. Now, what happens is when you have measurement equipment that you are cooking up to 600 degrees Celsius for this long time, like 60 hours, eventually, things start to show wear and tear or damage if you keep things hot for that long time. And so we decided that, you know what, let's take measurement up to 60 hours and then we can extrapolate from there as to how long this data will last. So up to 60 hours, we were able to see nearly flat lines between the on and the off state of data, which is, for instance, the red lines and the blue lines of the data in the right graph on slide 20. And so when you extrapolate that information, we were able to project that up to 900 hours at 600 degrees Celsius, the data should not get lost. It will remain stable. There won't be any issues with the data. This is very promising, right? I mean, 900 hours. So if you are worried about losing the data, you will have to worry about refreshing the data once every 900 hours. That's perfectly reasonable. That's perfectly acceptable. Right? So the other thing to keep in mind, and going to slide 20, is that you can also read and write the data many, many times. This is much harder thing to achieve because every time you try to read and write data, you damage or cause defects within the material in any types of memory material. And so write endurance is typically hard to achieve. Like most memory at elevated temperatures won't even have a write endurance of like 5 times. Like you try to write data into a memory element 4 or 5 times, it will fail at even temperatures of 200 or 300 degrees Celsius. Here were able to write up to 1500 times at 600 degrees Celsius again with no major issues. So we think if you multiply 900 times 1500, the amount of total life cycle of memory that you can get in terms of time is huge. 900 hours multiplied by 1500, it's a very large number, right? So certainly for a mission on a Venus or a year-long mission or years-long mission in an continuously elevated environment, you shouldn't have a problem with this kind of a memory. So, what is the competition like? Going to slide 22, we want to understand what other memory technologies are out there that have tried to measure things at elevated temperatures. As you can see, there are various people have tried various things, but very few people have been able to go beyond 500 degrees Celsius. There are basically just two reports of memory devices at 600 degrees Celsius. One is that of a platinum wire resistive random access memory developed by the Suga group and in Chiba University in Tokyo, and second is our ferroelectric results. And the interesting thing about the Chiba group's result is their result cannot hold up for more than a few read cycles. So even though it is operates at 600 degrees C, and it has a decent on-off ratio, if you cannot read the information more than a couple hundred times or even a few tens of times and it dies after that, it's not very useful long term, right? So in that sense, the ferroelectric memory that we have is the most superior available out there. If you see on the graph C, we don't have the highest on-off ratio yet, but this is the problem. This is not hard to solve. As I told you already, we have solved this problem. Technically, it's a matter of writing it up and publishing it. And so, as a matter of fact, just yesterday we published a paper where at room temperatures we have shown how do you engineer these on-off ratios, and we have shown on-off ratios up to a few thousands in these kinds of ferroelectric diodes. Now it's a matter of making them on platinum or other high temperature metals and testing them at elevated temperatures, which is something we have already done and shown, but because we have not published it, I cannot mention these things or cannot mention values or details about them. But the blue point on slide 22 in graph C, which is further lower down, it can be easily raised up to get into the desired corner. So slide 24, the important thing over here is, as I said, silicon carbide is the king of high temperature electronics. The good news is that aluminum scandium nitride as a material can already be grown really well on silicon carbide. This is something that we also demonstrated last year, and we have shown very stable ferroelectricity in aluminum scandium nitride on silicon carbide. So it's fully monolithically integratable. So memory and logic transistors together can be on the same silicon carbide wafer substrate, truly opening up the opportunity in the coming years for making very powerful computing devices or processors to operate in these extreme environments. Our view is that it opens up a whole new opportunity in products and technology, right? If you can tell people that, hey, now I can do computing in the most crazy conditions, the new opportunities for products for applications will open up. Some of them are pretty clear, which is in aerospace and space and nuclear power reactors, downhole drilling, automotives, and so on. But there may be many other opportunities that may just open up that we don't know of. Okay. So to summarize on slide 25, I want to mention something quite important, which is if you look at this graph, it's again feature size versus years. It's very reminiscent of Moore's law, that black dashed line that is going down constantly as a function of time. That's your Moore's law. And Moore's law actually has worked quite well for silicon. Okay. But if you look at high temperature technologies, the Moore's law does not quite hold because temperature is the king, or temperature is the main factor for high temperature technologies. So if you look at high T silicon on insulator or high T silicon technologies, they are stuck at 180 nanometer or 350 nanometer nodes. Right. This is quite interesting because even if you want to shrink the nodes, it may not be possible because temperature is going to ruin your device performances. So you need a certain width and length and size of devices to be able to operate at certain temperatures. So, for instance, if you look at the silicon carbide JFET technology of NASA, it's stuck at 3000 nanometer. To give you a perspective, silicon was at 3000 nanometer in the year 1980, way before I was born. So, silicon carbide, or for example, high temperature computing, or 800 degrees Celsius, 900 degrees Celsius computing, is today where silicon was in 1980, right? And I don't know if we will be able to develop uh, ways to make fabricate these devices that can follow Moore's law for these extreme environments. In other words, what I would like to say is that Moore's law works because most of our computing that we try to do is at room temperatures, and we are not a bit too worried about elevated temperatures, extreme environments. But in extreme environments, the conditions are so harsh that maybe it's not even possible to do Moore's law or Moore's law type progression. So, how would you, in fact, scale computing in these environments? And to that, my answer is I think you will have to leverage the power of memory. So, your transistor power will be limited because you are limited to a smaller density, larger size of transistors back which was available in 1980s, for instance. And so, you will have to figure out more clever ways to do computing or computing with memory and things like that, things that we have demonstrated earlier, as I was telling you about, and I have spoken about in the previous quantum photonics, one of the previous quantum photonics sessions. Right. So that's where we stand. Just to summarization sentences are that aluminum, scandium nitride ferrodiodes can be extremely promising for high temperature extreme environment memory. We have demonstrated them for 60 hours at 1 million read cycles at 600 degrees Celsius. And the next steps, what we can expect over here are full computing demonstration, compute and memory demonstration in high temperature, high radiation environments. Hopefully, it'll happen in the coming year or so, given how we are progressing in the lab. So, with that, I'd like to thank you all on slide 26. The green highlighted papers are the ones that I've talked about today or touched upon. The main paper, of course, is the Nature Electronics paper. There are also this archive preprint of the review paper that I posted and the paper that came out yesterday. Its DOI is also posted. It's appeared in ACS Nano. So with that, I'd like to thank you all again. I'll be happy to take questions for the next about 10 to maximum of 15 minutes. Thank you all.
Yeah, thank you so much, Deep. And I see Frank here on the audience. I think he came in late. So we would like to announce to the audience that we are opening the floor for questions. So please raise your hand and ask a question if you have. uh, Deep will not have so much time to be with us now, but it's a privilege to be able to ask him a question. So, or have some clarifications with him. So we'd like to welcome Frank, who just came in on stage. He's one of our regular moderators here in Quantum Photonics. So, hi, Frank. So, anyway, Deep,
Hello, Sophia.
yeah. Do you have a question?
Sure. Yeah. Our beloved, speaker, longtime speaker, Deep. Welcome again. Yeah, it's again another great talk, and congratulations for the new results. Very, already very proved scientifically, right, in the community, well received. For one question that I have, since time limited, could you go a little bit more on the explain a little bit more why this particular structure. I guess it's the German colleagues that initiated it. But in terms of outlooks, any other uh, possible candidates that can be even better? The
Yeah, it's a good question. It's let's go back to slide 9. On slide 9, I was showing you there. This is a full class of materials. This is no longer just aluminum scandium nitride is not just one material. There is a whole class of 3 nitride or wood site type ferroelectric materials. There is zinc magnesium oxide as well. There is gallium scandium nitride. There's aluminum boron nitride. There is aluminum yttrium nitride. There are like 5, 7 of these different classes of materials that have been found. We don't know which one is going to be the best material among this, to be very frank and honest with you. For high temperature applications, you have to consider several things. So even if a material appears better than aluminum scandium nitride at room temperature, you have to consider the elemental stability of its elements at elevated temperature. For instance, somebody may say, oh, what about zinc magnesium oxide or gallium scandium nitride, right? It may appear better than aluminum scandium nitride at lower temperatures because the coercive field is lower. The issue is zinc and gallium will diffuse quite readily at elevated temperatures, making it a nightmare to maintain ferroelectricity or appropriate composition. So not only you want superior composition, but then various thermodynamic mechanisms start kicking in at elevated temperatures. And my view is that scandium is a very high temperature stable metal. Aluminum itself is not a high temperature stable metal, but aluminum, when combined with nitrogen, is an extremely high temperature stable metal because aluminum nitride is one of the most well known refractory materials. And the last one is aluminum boron nitride, and I think there is no reason to believe why that one also won't be as good as aluminum scandium nitride. I think it comes down to the issue of which one you can manufacture. You can manufacture at scale. You can make thin films out of at scale and high quality thin films out of. And given all of those considerations, I think aluminum scandium nitride, with some variable composition, we don't know which exact composition of aluminum versus scandium will be good for which application. Some of this stuff is also proprietary. Is the best bet so far, given all the other factors considered, given its compatibility with manufacturing, given its ability to form thin and nice films, and so on. So most of these are sort of engineering things that you have to keep in mind. Does that make sense?
yes, yeah, very make a lot of sense. Yeah, thank you.
Yeah, thank you, Frank. And yeah, I take this opportunity, Deep, to congratulate you with your new baby because we haven't congratulated you yet. So, yeah,
Oh,
congrats
thank you.
from Quantum.
Appreciate that.
And I'd like to mention that Sergey Kalinin, I think is very keen on looking at your work because he just liked our post in X about your work, and I think he's been listening to the rooms that you were a guest in. So uh,
Okay, good.
anyway,
No, I know Sergey
anyway,
quite well. He's a very eminent and well-respected figure in the community, and we've had some very nice exchanges. We've tried to write grants together, things like that. So,
yeah. So I just noted that he liked our post that you are here. So yeah, um, yeah. He told me before that he was listening to one of our rooms with you here. So anyway, we have Kevin here. Kevin, do you have a question?
Oh yeah, yeah. Since time is short, thanks for the presentation. All I can think of is, does this? Do you know if this has to do with hafnia? You know, uh, yttrium doped, hafnium dioxide. For any of this.
yeah, so all versions of hafnia, yttrium doped, silicon doped, or zirconium doped, they will lose ferroelectricity at some 400 degrees Celsius or something like that. So they were also tried as candidates in the past, but none of them succeeded. I think the central issue with hafnia is a different one, which is maintaining ferroelectric phase in a hafnia or any of the hafnium compounds, the doped ones, yttrium doped, silicon doped, zirconium doped, is a tough call. That's because there are so many various structures, crystal structures of hafnia available, and only one of them, which is the orthorhombic phase, is the ferroelectric phase. And so, while hafnia is extremely promising for very thin films of ferroelectric material and lower coercive fields, I think for high temperatures, I don't think it stands a chance as compared to the nitrides.
Oh, okay. Thanks. And maybe another thing I can think of is you might have mentioned this integrating this memory with high temperature processors could lead to memory enhanced compute chips for data intensive AI applications. Is that correct?
Yeah, that is correct. Yes.
Okay, yeah, and since I guess um, congratulations with your baby. It's so awesome. And the only thing I'll say is check out ultramagnetism if you haven't looked that up.
Okay, I will.
Yeah, thank you, Kevin. So I think we should not keep Deep for a long time. We will try to invite Deep again whenever it's convenient for him, because I'm sure that he has a lot of other parallel papers which are all benchmarking and amazing that are happening right now. So he will have a lot to talk to. But in the meantime, let's give him some little more free time to spend with his baby. So I'd like to ask Bob if Bob has something to say, and then after that, we will pass the mic to Darcel. And thank you, Frank and Kevin, for coming up on stage. So, yeah, I'd like to thank Deep also for coming here. And please don't get tired of being our guest speaker in quantum photonics. So, do you have some last minute message to the people here in quantum photonics?
No, just thank you again for hosting me. I think it's always great to chat up with this community and get your perspective. And happy to come here again when I have something more new and interesting to talk about. So keep all this going. It's always nice to have these conversations in a broad cross section of the community. So I'm glad you people keep doing it. Cecile, Darcel, Bob, all of you. So thanks again.
Yeah, to everyone, please follow Deep in Twitter. He is in Twitter. You can just search for him in order to be updated about his works. It's always very exciting because there's always something new. So, thank you, Deep. And now I'd like to give the mic to Bob if he has something to say before we close the room.
Just on behalf of everyone in the audience, thank you for another spectacular discussion, and I look forward to your return.
Thank you, Bob.
Yeah, all right, Darcel. So let's close the room now.
Thank you, Cecile. And thank you, Deep. I'm sorry, everyone. I've got the hiccups, but I'll try to get through it. And congratulations on your newborn. Um,
Thank you.
so, to close the room, we're going to start our countdown from lucky number six. Is everybody ready? Ready?
Ready?
Ready?
Six.
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 Kevin, five.
Fiverr.
Frank, cuatro.
Quattro it is.
Bob, tres.
Three it is.
Cecile, dos equis.
Dos Equis.
Deep, welcome back, and we want to see you again. And you are numero uno. Call out our last number, please.
Uno.
Thank you so much, Deep, and thank you,
All right.
everyone. See you on the next rooms.
Take care.
Please check out. Monica Anderson will be with us, I think, next time. This is the next room, and she will be talking about alignment of LLMs and also jailbreaking. And once again, thank you, Deep, and good night, everyone.